These are the notes for AP Calculus on the topic of concavity. So concavity refers to the shape of a graph other than something that's linear. So when something's concave up, it looks something like this. A little mnemonic device to help you remember that is shaped like a cup. Concave up, shaped like a cup. And what's really happening when something's concave up is the first derivative is increasing. So if we look at our first derivative on this graph, as we go from left to right, you can see right here the slope on the tangent line would start out being negative, and as we head this way, the slope is still negative, it gets less and less negative, so it's actually increasing until right there the slope, or first derivative, is 0, and then the first derivative starts becoming a little bit positive, more and more and more and more positive as we go this way. So as we head from left to right, when something's concave up, the slope is increasing. And that means the first derivative is increasing, because the first derivative is the slope. So that must mean the second derivative would have to be positive. The second derivative is positive because it's the derivative of the first derivative, right? Just like the first derivative tells you whether the original function is increasing, the second derivative tells you whether the first derivative is increasing or decreasing. So if the first derivative is increasing, the second derivative must be positive. So in any case, it's concave up. Similarly, something that's concave down, like this, the mnemonic device to help you remember that would be shaped like a frown. Concave down, shaped like a frown. And here the first derivative would be decreasing. So if we look right here, we can see the slope starts out being positive. It's still positive, it's getting less and less positive, so it's actually decreasing until right there the slope is 0. And then the slope of the tangent line starts becoming negative, more and more and more and more negative. So as we head from left to right, the slope, or first derivative, keeps decreasing. That's what makes it concave down. And if the first derivative is decreasing, the second derivative must be negative, because it's the derivative of the first derivative. Just like the first derivative tells you whether the original function is increasing or decreasing, the second derivative tells you whether the first derivative is increasing or decreasing. And another thing to help you guys remember which one goes with which is if the second derivative is positive, it's concave up, so you can put a little positive sign there. And if the second derivative is negative, it's concave down, so you put little negative signs there. Now, if something's not concave up or concave down, the last option is that it's linear. So linear should be a straight line like that. If something's linear, that means the first derivative is remaining constant. A linear graph has a constant slope. It's the same slope all the way across. And if the first derivative is constant, the second derivative must be 0 for that to be the case. So you can see that would be true of any linear function. For instance, let's say y equals 3x minus 1. There's a linear function, right? The first derivative, dy dx, would be 3, and the second derivative would be 0. You can see that would be true of any linear function, because the first derivative is always going to be a constant, and the derivative being constant by itself is 0. So let's take a look at what this looks like graphically here, what concavity looks like. And we'll start with a graph that switches concavity quite often, and that's the graph of f of x equals sine x. So here's the graph of sine x right here. And then the derivative of sine, f prime of x, is cosine. So here's the graph of the derivative, cosine. So let's put a number line right underneath that. And let's see what the first derivative tells us about the original function. So this part's a little bit review here. So f prime of x, you can see, well, where would our critical numbers be? Well, our critical numbers, remember, are where the first derivative is 0 or undefined. Well, it's not undefined anywhere, but it is 0 right there, 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 and there. Don't worry about the exact values right now. They'd all be in terms of pi. These are trig functions. But right there, 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 and there. So that's where our first derivative is 0. And then in between there, to see if it's positive or negative, you could test in the equation, but here it's easier to just look at the graph. So what we were really looking at when we saw those are the places where the first derivative is 0 is the y values, the y coordinate 0. So for this number line here, we're going to be looking at the y values, whether they're positive or negative. In other words, is the graph above or below the x-axis? Here, these y values are all positive y values above the x-axis there, a little bit, and then these are all negative y values. Then back to positive y values, and then negative y values. So what this shows us about the original function, f of x, remember this is the slope of the original function, so we can see it's increasing when its first derivative is positive, decreasing when it's negative, back to increasing when it's positive, and back to decreasing when the first derivative is negative. And we can see that on our graph if we look. You can see the original function increasing just a little bit, then it's decreasing, then increasing, then decreasing, just like our number line shows. So we did that part before, but now let's take a look at what the second derivative tells us. So, if we go beyond this, the second derivative, well, the first derivative was cosine. Remember, the derivative of cosine is negative sine. So here we've got the graph of negative sine x. And again, let's draw another number line right underneath this. This time it's going to represent the second derivative. So f double prime of x. Okay. So let's see where the second derivative is 0 are defined, kind of like we did the first derivative. You can see the second derivative is 0 right there, right at the origin right there, and right there. So I'm going to mark those off. Again, this would be like -5, but we're not concerned about the exact values right now. So at those three places, the second derivative is 0. And again, in between there, since we have the graph of the second derivative right above it, all we have to do is look at its y values to figure out where it's positive or negative. Okay. So the y values here start off being negative. Then in between here, all these y values are positive. Then here they're negative, and then back to positive. So this actually tells us a couple different things. It tells us something about the first derivative, and it tells us something about the original graph. Let's first take a look at what it tells us about f prime of x, our first derivative. Well, it's similar to what the first derivative told us about the original function. Remember, the first derivative is the slope of the original function, f of x. In the same way, the second derivative is the slope of the first derivative. So when the second derivative is negative, that must mean the first derivative is decreasing. When the second derivative is positive, the first derivative is increasing. Negative back to decreasing. Positive back to increasing. And we can see that when we look on the graph of the first derivative. We can see it's decreasing right there, and then it's increasing, decreasing, and then increasing, just like our number line shows. So it does tell us that, and that's useful. However, what we're going to focus on today is actually what the second derivative tells us about the original function, f of x. And that goes back to what we saw before. Remember, we said when the second derivative is positive, it's concave up. The first derivative is increasing. And when the second derivative is negative, it's concave down because the first derivative is decreasing. So the second derivative is negative, the first derivative is decreasing, that means it's concave down. I'll just abbreviate it CD. The second derivative here is positive, the first derivative is increasing, so here's the graph of the original function is concave up. Second derivative back to negative, concave down, back to positive, concave up. So let's look at our graph of the original function to see how that fits in. You can see the graph is concave down, so right there. And it's concave up, shaped like a cup until right there. Back to concave down, shaped like a frown right there, and then back to concave up. And these 3 points here, where the graph switched concavity, have a special name. So those points where a graph switches concavity are called points of inflection. Or sometimes inflection points. Same thing. So, unlike relative mins and maxes where it matters whether it switches from positive to negative or negative to positive, they have different names for them. Here, these are all just collectively referred to as points of inflection, regardless of whether the second derivative switches from negative to positive or positive to negative. The key is if it switches sign and the function is continuous, there we have a point of inflection. So to figure out our possible points of inflection, it's very similar to how we found critical numbers using the first derivative, except now we're using the second derivative. So these are the values that will make the second derivative either 0 or undefined, are the possible points of inflection. And we saw before, in intervals in which the second derivative is positive, greater than 0, indicate f of x is concave up. Intervals in which the second derivative is negative, less than 0, indicate f of x is concave down. And definition of points of inflection, if a function changes concavity from concave up to concave down, or from concave down to concave up at a possible point of inflection, then there actually is a point of inflection at that possible point of inflection, assuming the function is continuous there. So again, it just has to be continuous in order to be a point where it switches concavity in. All right, let's take a look at some example problems now. This one says, state the interval or intervals on which the graph of the function is concave up and concave down, and the coordinates of any points of inflection. So, both of those come from the second derivative. Let's go ahead and take the first derivative first. So f prime of x would be 12x minus 4x cubed. And then the derivative of that, f double prime of x, would be 12 minus 12x squared. In this case, you can see the second derivative wouldn't be undefined anymore, but it could be 0. So we set it equal to 0, find our possible points of inflection. Factor out the 12 as a GCF. Do this with 1 minus x squared. And that factors further. Using the difference of perfect squares, 1 minus x squared factors into 1 minus x and 1 plus x. So our possible, not abbreviated here, it's not an official abbreviation, just for convenience. Possible points of inflection. Well, 12 is never 0. One of these has to be 0. What would make this one 0 would be x equals 1. What would make this one 0 would be x equals negative 1. So we have two possible points of inflection. Just like our critical numbers are possible places where you have relative external. But until we draw our number line, we don't actually know if they actually are points of inflection. So the next step is to draw your number line. But this time, we're going to label it f double prime of x. So we're testing into the second derivative here. And we've got negative 1 and positive 1. And both of these made the second derivative equal to 0. So here we get test something less than negative 1, like negative 2. 1 minus negative 2 becomes 1 plus 2, that's positive. 1 minus 2 is negative. Positive times a negative is negative. In between negative 1 and 1, 0 is part of the easiest thing to test. 1 minus 0 is positive. 1 plus 0 also positive. Positive times positive is positive. Anything greater than 1, like 2. 1 minus 2 is negative. 1 plus 2 positive. Negative times positive is negative. So this shows us that f of x, when the second derivative is negative, would be concave down. When the second derivative is positive, concave up. Second derivative negative, concave down. So we can write down the concave up and concave down intervals. We can say f is concave up on negative 1 to 1, and f is concave down on the interval from negative infinity to negative 1. U for union, also the interval from 1 to infinity. And now we can actually look at our number line and see if the possible points of inflection actually are points of inflection. The negative 1, well, the second derivative does change sign. It does switch from concave down to concave up. So that is a point of inflection. And at 1, the second derivative changes from positive to negative. It switches from concave up to concave down. So that's also a point of inflection, since it switches sign, second derivative, and changes concavity. So, let's write that down. It said find the coordinates of any points of inflection. That means we also need their y coordinates. So let's go find the y coordinates, plugging them back into the original equation. So if we go f of negative 1. Actually, in this case, we can plug them in at the same time because it's an even function. Plug in positive and negative 1 simultaneously. It would be 6 times plus or minus 1 squared minus plus or minus 1 to the whole. either positive or negative 1 squared is 1 times 6 is 6, minus positive or negative 1 to the fourth is 1. 6 minus 1 gives you 5. So that's the y-coordinate for both of them. So they have 1, 5, and negative 1, 5. So we can say F has points of inflection at 1, 5 and negative 1, 5. Notice when I write down the final answer, I don't abbreviate. Keep on concave down and points of inflection, I write it out. Because these are not official abbreviations here. These are just for our convenience to use on our number lines, so there's not as much to write down, and so it fits better on the number line. Alright, now let's take a look at the next one. This one says consider a differentiable function f. That just means that you can find its derivative with a given first derivative. So it gives you the first derivative already. Find the x-coordinates of the inflection points and state the intervals, or intervals on which the f is concave up and concave down. So this time, we've already got the first derivative. So unlike the first problem, where we had to take the derivative twice to get to the second derivative, here we already have the first derivative, so we only have to take the derivative once to get to the second derivative. So f double prime of x, well, let's see what rule we'd have to use here. We've got, you could multiply this all out, but it's a lot easier if you don't, and instead just leave it like this, and treat the first one as x squared, and the second one as x squared minus 4 cubed, and use the product rule overall. Okay, so remember the product rule, we have the derivative of the first one, derivative of x squared is 2x, times the second one as it is, squared minus 4 cubed, plus the first one as it is, x squared, times the derivative of the second one. Use the power rule, but also because there's a function inside, you also have to use the chain rule. So using the power on the outside, that would be 3 x squared minus 4 squared times the derivative inside is 2x. And then to make this simpler, to make it easier to find our possible points of inflection, let's go ahead and use factoring. So if you think of this, it's our first term, 2x times x squared minus 4 cubed, plus, here's our second term. Those are all both going together. Let's see what those have in common as a GCF we can take out. Well, they both have an x, we can take that out. And they both have x squared minus 4, and the lower exponent is squared. So we'll take out x squared minus 4. And let's see, I think there's one more thing we can take. Oh yeah, we can take out a 2 also. This has a 2 and that has a 2. So we got a 2x and an x squared minus 4 squared. Okay. Now let's see what's left in parentheses. Well, the 2x is gone here. This was x squared minus 4 cubed, so we just have one of those left, x squared minus 1. And since it's just to the first power, we don't need the parentheses around it, or the exponent of 1 row. And then plus, what's left of the second term? Let's see, we've got this completely gone. The 2x is gone, so all that's left is this 3 and this x squared. Okay, let's keep simplifying that. F double prime of x, we've got 2x, x squared minus 4 squared, and then if we combine our like terms here, 3x squared and x squared gives you 4x squared, and then minus 1. Now you can do some more factoring. Notice you can take out a GCF of 4 out of those and bring it out in front with a 2x to make it 8x. So F double prime of x equals 8x, and then you want, let's just leave this like this one for now, x squared minus 4 squared, and then what's going to be left here is x squared minus 1. We can factor 4 out of it. So we've got 8x. Now for this x squared minus 4 squared, notice that would factor into x minus 2x plus 2 if it wasn't squared, right? But there's 2 of them, right? Squared, so you're going to have 2 of each, 2 of the x minus 2s and 2 of the x plus 2. So if you want to make it easier, you can factor x minus 2 squared and x plus 2 squared. And then x squared minus 1 factors into x plus 1 and x minus 1. Squares. So we have a lot of possible points of inflection this time. And the second word makes the second derivative 0 or undefined. In this case, again, it can't be undefined. So the possible points of inflection would be x equals, well, so 8x equals 0, that would be 0. And 2, -2, -1, and 1. So we've got 5 possible points of inflection, but we won't know if they actually are points of inflection until we put them on the number line and test. So let's go ahead and do that. So label your number line f double prime of x, again, the second derivative. And we've got -2, -1, 0, 1, and 2. And all of these make the second derivative equal to 0. So what can we test here? But before we test something over there, let's see if we can find any shortcuts that can make our testing a little bit easier. Well, take a look. We've got a square there and a square there. Something's raised to an even exponent is never going to be negative, so we don't have to worry about testing in those. We just have to worry about 8x, the x plus 1, and the x minus 1. So if we test -3, for instance, -3 times 8 makes that negative. -3 plus 1 is negative. -3 minus 1, negative. 3 negatives multiplied together is negative. Between -2 and -1, you can use -1.5 or -1.5. Makes this one negative. -1.5 plus 1 is negative. -1.5 minus 1, also negative. 3 negatives multiplied together, still negative. Between -1 and 0, you can test -1.5 times 8 is negative. -1.5 plus 1 is positive. -1.5 minus 1, negative. 2 negatives times a positive is positive. Between 0 and 1, you can test 1/2, 0.5. 1/2 times 8x is positive. 1/2 plus 1 positive. 1/2 minus 1 negative. 2 positive times a negative is negative. Between 1 and 2, you can test 1.5 or 1.5 times 8 is positive. Plus 1 is positive. Minus 1.5 minus 1 is positive. 3 positives multiplied together is positive. If you test something greater than 2, like 3 times 8 would be positive. 3 plus 1 positive. 3 minus 1 positive. 3 positives multiplied together is positive. So this shows us that f of x, when the second derivative is negative, is concave down. Still negative, still concave down. Positive, concave up. Negative, concave down. Positive, concave up. And still positive, concave up. So we can answer the first part, state the intervals on which f is concave up and concave down. Actually, that's the second part of the question, but let's go ahead and answer that first. So we can say f is concave up on -1 to 0. With, here we can go 1. And since it's just 0 at 2, we don't have to stop at 2. We can go 1 all the way to infinity. If it was undefined, then you would have to stop here. And f is concave down on negative infinity. Again, we don't have to stop at -2 because it's 0. So you can do negative infinity all the way to -1, union with 0 to 1. And let's see if our possible points of inflection are points of inflection or not. Alright, so -2. Is that a point of inflection? Well, the second derivative doesn't change sign there. It stays concave down, so no, it's not. -1, the second derivative does change from negative to positive. It switches concavity, so that would be a point of inflection. At 0, the second derivative changes sign again, so it's from concave up to concave down. That's also a point of inflection. At 1, the second derivative changes from negative to positive, goes from concave down to concave up. So that's a point of inflection. At 2, the second derivative doesn't change signs, so it's not a point of inflection. So out of the 5 possible points of inflection, only 3 of them actually turned out to be points of inflection. So we can say f as, and here it calls it inflection point, same thing though. Just use the same wording here in my answer. Inflection points. And it only asks for the x coordinates here, so we don't have to go back and find the y coordinates on this one. So you say at x equals, and we've got 3 of them there, so you can say, list them off in brackets, -1, 0, and 1. So I got brackets bracing. Okay, let's take a look at the next one. Next one, again, a little different. Consider a differentiable function f with a given second derivative. Find the exponents of the inflection points and the state intervals on which f is concave up and concave down. So here, these are the easiest ones of all in some ways because we already have the second derivative. We don't have to take the derivative again because that would be the third derivative. We just need the second derivative and we have it. So you just set it equal to 0. It won't be undefined anywhere. And just see, it's almost completely factored except for this x squared minus 9. So let's factor that further in x minus 3 and x plus 3. And again, let's use that to find our possible points of inflection. So we'll make this first one 0, it'll be x equals 0. We'll make this factor 0. Notice the fourth doesn't matter in terms of what makes it 0. What's inside of 0, an exponent of 4 is going to make it 0 also. So if you set 2x minus 3 equals 0, you add the 3 divided by 2, so you get x equals 3 halves. Set x minus 3 equals 0, you get x equals 3, and set x plus 3 equals 0, you get x equals negative 3. So those are our 4 possible points of inflection, but again, we won't know if they actually are points of inflection until we put them on the number line test. So let's put them in order. We've got negative 3, got 0, 3 halves, and 3. So that was f double prime of x. All of these make the second derivative 0. There's no denominator here for it to be undefined. And let's go ahead and test before we do that and see if we can find any shortcuts. Again, I notice there's an even exponent of 4 there, so we know that's never going to be negative, so we don't have to worry about testing there. So let's say we test negative 4. Negative 4 cubed is negative, but times the negative 2 makes it positive. Negative 4 minus 3, negative. Negative 4 plus 3, negative 2. 2 negatives times a positive, it is positive. Between negative 3 and 0, you can test negative 1. Negative 1 cubed is negative, but times negative 2 makes it positive. Negative 1 minus 3 is negative. Negative 1 plus 3, positive. 2 positive times a negative, it is negative. Between 0 and 3 halves, you can test 1. 1 cubed is 1 times negative 2, and negative. 1 minus 3, negative. 1 plus 3, positive. 2 negatives times a positive is positive. Between 3 halves, which is 1 1/2 and 3, you can test 2. 2 cubed is positive, but times negative 2 makes it negative. 2 minus 3, negative. 2 plus 3, positive. 2 negatives times a positive is positive. And here you can test 4. Cubed is positive, but times negative 2 makes it negative. 4 minus 3, positive. 4 plus 3, positive. 1 negative times 2 positives, it is negative. So this shows us that f of x is concave up. One second is positive, concave down, one second is negative, back to concave up, and then back to concave down. So we can say f is concave up on negative infinity to negative 3, union with 0. And you don't have to stop at 3 halves because it stays concave up. I mean, because it's 0 right there. So 0 to 3. And f is concave down on negative 3 to 0 and 3 to infinity. And let's take a look at inflection points, see if those possible points of inflection actually turned out to be points of inflection. So at negative 3, the second derivative does change sign, so that's a point of inflection. At 0, the second derivative changes sign, that's a point of inflection. At 3 halves, the second derivative stays positive, stays concave up, so that's not a point of inflection. And at 3, the second derivative changes sign, so that is a point of inflection. So we can say f as inflection points at x equals negative 3, 0, and 3. Just ask for the x coordinate. Now let's take a look where it just says state the x-coordinates of any points of inflection, put key difference here, justify your answer. And notice we're back to starting with the original function, g of x. So, we need to find the derivative twice to get the second derivative. So first of all, we got 2x, right, times 4x minus 1 cubed. So to take the first derivative, g prime of x, that's going to involve the product rule. So the product rule, what we go first is the derivative of the first one, that would be 2, times the second one as it is, 4x minus 1 cubed, plus the first one as it is, 2x, and then we take the derivative of the second one, we also need the chain rule, because we have a function inside there. So on the outside, you use the power rule, so bring down to 3, so it'd be 3, 4x minus 1 squared, times the derivative inside using the chain rule, the derivative inside is just 4. But remember, our objective is to get the second derivative. So you could try to take the second derivative from here, but usually it's easier if you make the first derivative as easy as possible, simple as possible, to make our second derivative a little bit easier to work with. So let's just go ahead and simplify it, g prime, the first root. Again, the technique we can use here is factoring out the GCF. So what do those two have in common? They both got a 2 we can factor out as part of the GCF, and they both have 4x minus 1 squared. And let's see what we have left when we take that out. Well, the first term, all that's left is just one of those 4x minus 1s because it was cubed. And then plus, what's left of this term, we've got, this is completely gone, 2 is gone, so we've got 4 times 3 is 12. And then we've got x, and that's it. The 4x minus 1 squared is gone, and so is the 2. So let's just make this as simple as possible before we take a second derivative. So we've got 2 times 4x minus 1 squared. And if we simplify this one, that's 4x plus 12x is 16x minus 1. So that's our first derivative. Now let's take the second derivative. Again, you can see we're going to need to use the product rule. Treating 2, 4x minus 1 squared as your first function and 16x minus 1 as the second function. Multiply together. So g double prime of x, using the product rule, would be the derivative of the first one. Using the power rule, that'd be 4x minus 1 to the first, but we also need the chain rule on that because there's a function inside 4x minus 1. So that'd be times the derivative inside is 4. Okay, so that's the derivative of the first one, and the product rule says times the second one as it is, 16x minus 1. And then plus the first one as it is, 2 times 4x minus 1 squared, times the derivative of the second one is just 16. So let's go ahead and take out our GCF now. Make this simpler. So what do these have in common? Well, let's see. They both have 16, right? 4 times 4, so we do 16. And they both have a 4x minus 1. Take that out of the GCF. And let's see what we have left of each term. Well, what's left of this term? 16 is gone, 4x minus 1 is gone, so all that's left is that 16x minus 1. Plus, what's left of this term? Well, we've got the 2 is still there. We took out the 16, but that 2 is still there. And it was 4x minus 1 squared. We took out one of them, so we still have 1 4x minus 1. And let's go ahead and simplify this. So I've got 16, 4x minus 1. And then if we distribute out this 2, that's going to be 8x minus 2. And then we can combine the like terms. 8x and 16x gives you 24x. Negative 2 and negative 1 add to negative 3. And you could leave like that, or there's a little bit more factoring we could do. Notice you can factor out a GCF of 3 out of there times the 16 gives you 48. And 4x minus 1. And after we factor out the 3, what's left is 8x minus 1. It just makes it a little easier to tell the possible points of inflection and also when you're testing. So here are possible points of inflection. 48 can't be 0, so it'd be x equals, we set 4x minus 1 equals 0, add the 1 divided by 4, 1/4. We set 8x minus 1 equals 0, add the 1 divided by 8, so x equals 1/8. So those are our two possible points of inflection. So now we just want to put those on the number line and see if they actually are points of inflection. We got 1/8 and 1/4, so they're pretty close together here. G double prime of x. Both of these make the second root of 0. And over here we could test 0. 0 minus 1, that's a negative. 0 minus 1, negative. Negative times negative is positive. The one that might be a little trickier to test is between 1/8 and 1/4. That's a pretty small interval there. So something in between, you could try 1/5 or 1/6 or 1/7. So let's try 1/5. Well, 1/5 times 4 would be 4/5 minus 1, that'd be negative. But 1/5 times 8 would be 8/5, which is bigger than 1, minus 1, so that'd be positive. Negative times positive. Negative. And greater than 1/4, you can test 1. 1 times 4 is 4 minus 1 is positive. 1 times 8 is 8 minus 1 is positive. Positive times positive is positive. And we could write down where it's concave up and concave down, but it's not asking us to state the intervals, just the points of inflection, x-coordinate, and justify our answer. So we can tell just from this, notice at 1/8, the second derivative switches from positive to negative, so that's a point of inflection. And at 1/4, the second derivative switches from negative to positive, which is sine, so that's also a point of inflection. And it just asks for the x-coordinates, so we can state G this time as points of inflection. At x equals 1/8 and x equals 1/4. And to justify our answer, it's similar to how we justified relative minimums and relative maximums, but we're using the second derivative. And also, notice for points of inflection, as long as it changes sign, it doesn't really matter what it's called, whether it goes from negative to positive or positive to negative. Unlike relative mins and maxes, it matters. Going from positive to negative, the first derivative is the relative max, negative to positive on the first derivative, the relative min. So here we can just say, since G double prime of x changes sign at x equals 1/4 and x equals 1/8. And that concludes the notes for AP Calculus on the topic of concavity and points of inflection.